Okay. So, human language is very impressive. Indeed, although impressive in their own right, no other naturally occurring communication system we see in nature appears to have the sheer amount of expressive power exhibited by human language. Despite this, however, the field of human language research has traditionally been one based on dichotomies. How much of the human language faculty can be attributed to some kind of genetic endowment versus how much can be explained by other methods such as statistical learning. How much of linguistic structure is the result of said structure, often some kind of adaptive advantage to early hominins, versus how much is the result of language itself actually evolving in accordance with language users' brains. It is perhaps more beneficial, however, to instead of viewing these as dichotomies, view them as examples of complex gene-environment interactions. And in doing so, we begin to see how human language can perhaps be seen as an emergent phenomenon of three interacting systems. The biological system refers to all the phylogenetic adaptations that are necessary for the human language genome to evolve. Now, these adaptations obviously evolved in accordance with known biological pressures. Therefore, it is safe to conclude that they had a non-negative impact upon natural selection. The ontogenetic system refers to the way in which an individual's language develops and changes throughout the course of their lifetime, and how they adjust their knowledge continuously in accordance with their environment. The cultural system refers to the way in which human language is quite clearly impacted by social and cultural transmission. This is exhibited by the way in which language is in a continual state of flux, and by such things as the way in which the meanings of individual lexical items can change incredibly quickly within literally a single generation. The basic idea here then is that there is perhaps some kind of genetic endowment, some kind of genetic instinct to learn language. We as individuals then learn language, but then our own individual biases impact language in such a way that through our usage we alter the environment around us, which can then perhaps exert pressures back on the biological system. Now, the work I'm going to present to you today is primarily concerned with this part of the system here, the cultural aspect, and specifically relates back to something I mentioned a minute ago, specifically the idea that perhaps certain aspects of human language evolved, not due to its utility to us, but because it offered an advantage in preserving the language itself. This idea was first put forward by Simon Kirby and his group up in Scotland, and has been explored extensively through the concept of iterated learning. Now, the basic idea here is that we have an agent in the first generation. Let's call him Bob. We give Bob some meanings. Now, for each one of these meanings, Bob produces a signal. These meaning-signal pairs then form a set of utterances. These utterances are then used to train the agent in the next generation. Let's call her Susan. Susan learns her language solely from exposure to Bob's utterances. And after she's been trained, Susan is then given some meanings, and she also produces signals, and she then produces a second set of utterances. Now, the key thing to remember here is that Bob's and Susan's utterances are going to be different, perhaps not just because they were given different meanings to convey, but because their own individual biases have resulted in them favouring certain signals with specific meanings over others. After this, then Susan also passes her utterances on to train the next generation, is given meanings, signals, utterances, and so on and so forth. Now, this concept captures a very important aspect of language, namely the linguistic bottleneck. As far as iterated learning is concerned, the linguistic bottleneck refers to the number of utterances each agent is given to learn the languages from. So say the bottleneck is around about 50, that means Susan was given 50 utterances produced by Bob in order to learn her language. More theoretically, it refers to the idea that language exists in sort of essentially two planes of existence. The internal aspect, version inside our heads, consists of mappings from meanings to signals. But then also language, quite clearly, like I said, has this external aspect to it, through its very usage. The idea here is then that language persists from one generation to the next through continual mapping from this I language, internal, to the E language, and then back again. This essentially creates a bottleneck on the flow of information within the system, and this bottleneck will then have an eventual impact upon this linguistic structure, in much the same way as a bottleneck on genetic information will have an impact upon the overall shape of an organism. Now, one phenomenon that is largely believed to be the result of this bottleneck is that of compositionality. The basic idea here is that the meaning of a complex expression is the result of the meanings of the individual parts and the way in which they're put together. Thus, the logic dictates, all we have to do as language users is learn the meanings of a finite set of expressions. That way, whenever we are presented with a novel utterance, we are able to deduce the meaning of said utterance by using the already learned expressions and grammatical structures. For example, you are able to work out what this sentence means because you know what a cat is, you know what a mat is, and you know what a lasagna is. If you don't know what a lasagna is, you've led a very sad life. But the idea here is that each of these individual expressions involves a mapping to a meaning inside your head, which invokes a specific meaning. The way in which the words are ordered then creates an overall meaning for the sentence, a meaning which is perhaps akin to a lovable cartoon character. Now, compare that to the second sentence, which I hope is novel to you, but despite the fact that it is novel to you, you're able to understand it for the exact same reason that you're able to understand the first expression, even though the meaning conveyed here is very, very different, and perhaps more akin to a Lewis Carroll-style acid trip than anything else. Now, I wanted to explore the relationship between the bottleneck and compositionality, and to do so I developed a model of iterated learning, one which was largely based upon a model originally put forward by Simon Kirby and Jim Herford. This model essentially has 4 key properties. A meaning space, which consists of 8-bit binary strings, so it's a mean space of 256 in length. A signal space, which is exactly the same as the mean space, 1 mature agent per generation, and 1 immature agent per generation. Agents here are feed-forward neural networks with 3 layers, 8 nodes in each layer, and they use standard backpropagation in order to learn. There are also a number of parameters. Like I said, there's the bottleneck, which here it takes the form of the number of utterances each immature agent is given each generation in order to learn their language. And then there's epochs, which, as I'm sure you're aware, is just the number of training sessions a neural network experiences. The number of training episodes given to each agent, each immature agent, is the result of multiplying the bottleneck by the number of epochs. So here, with a bottleneck of size 50, each immature agent is given 5,000 training episodes. In order to measure the success of this model, the authors developed 2 measures. The blue line here is expressivity, which is essentially the number of unique meaning signal pairings that an immature agent is able to produce out of a possible 250 after training. The red line represents the amount of difference between the mature's language and the immature's language after training. Now, the authors have basically show that this model depicts 3 different types of behaviour depending upon the size of the bottleneck. If the bottleneck is too small, the system remains highly unstable and completely inexpressive. If, however, the bottleneck is set too big, then yes, the system does learn, but only after a very, very prolonged period of time, such a length of time that's just silly. If, however, the bottleneck is set just right, we get the kind of behaviour we see here. Now, this is all well and good and all, but language does not exist in such a simplistic social setting, such as the one here, which is representative of that in the normal iterated learning model. Moreover, individuals are likely to learn their language from multiple tutors, some of which may not even be fully linguistically competent themselves. So, we developed a version of this iterated learning model, which consists of a population of, say, 50 mature agents and 50 immature agents per generation. This enabled us to assign multiple tutors to each immature agent. And as you can see here, if we assigned each immature agent 10 mature trainers and no immature trainers, the system learns better than it did before and also quicker as well. If, however, we assign 10 immature trainers and no mature trainers, then unsurprisingly, given how iterated learning works, the system never learns. And if the number of mature trainers is equal to that of immature trainers, then we see some learning occur. Like, it's not a perfect linguistic system by any measure, but there's definite learning happening there. And this is the same if this is for 5 of each trainer and 10 of each trainer. However, like I said, we were predominantly interested in compositionality. So we developed a measure of that, which basically involves looking at each bit of the signal and sort of being able to predict the rest of the bits in the bit strings after that. What you're then looking at here is the number of generations out of 50 that are fully fully compositional system was in place. Down in the bottom left here, you see the case for one mature trainer and no immature trainers, which is akin to that what we saw in the normal iterated learning, and essentially consists of 15 iterated learning models running in parallel. Top left there is the case in the second graph I showed you, where you have 10 mature trainers, no immature trainers, and you see it's very dark. What you then see here is this nice little split, where as the number of immature trainers starts to outweigh the number of mature trainers, we get less and less compositionality until we get nothing at all. Now, what about the bottleneck? Well, we decided to look at the impact of the bottleneck on compositionality. Now, this is the case for one mature trainer and no immature trainers, and each different colour is a different bottleneck size. Now, what's important to remember here is that the number of epochs here has been halved to 50. So compared to the normal iterated learning model, each of the agents here are only having half the amount of training episodes they did before. Which is why, if you look at the bottleneck size 50, which is the green one here, it sort of just bumbles around here, it doesn't really do much. Bottleneck size 80 seems to do well. But what do you think happens if we add more mature trainers? It learns. I mean, admittedly, if you look at bottleneck size 50, it's not a perfect compositional system, but there is definite learning occurring there. So, we wanted to make sure that, was it just the case that it was these the number of mature trainers that was having an impact, causing this effect on the system? And in doing so, we decided to look at the first 6 generations, because that seems to be where the main language learning occurs in the system. We decided to look at the first 6 generations of the model run. And what we decided to do was that each generation, we took an immature individual at random. We then measured its amount of compositionality going into the training session, and the amount of it, and its level of compositionality after the training session. If the level of compositionality afterwards was greater than that going in, then the episode was deemed to be a success. What you're then viewing here is the number of successful training episodes per generation. And the blue line is one mature trainer, the red line is 10 mature trainers. Although there's a little bit of iffiness in the first generation, which can be explained by the fact that in this first generation, each agent is given just random mean signal pairs just to seed the model, just to get it going. But by about generation 3, we start to see that having more mature trainers tends to lead to great benefits in terms of compositionality, a pattern that tends to continue. But why is this? Why does having more mature trainers cause this behaviour? It appears to be due to the fact that having more mature trainers leads to more signal variety in the system. What you're looking at here are the number of signals that were used over a run of 50 generations for various values of mature trainers. Got 1, 2 and 9 there, because I got bored of using the number 10 all the time. Basically, as you can see, out of all 256 possibilities, with high numbers of mature trainers, we start to see that more of the signal space is actually used to convey meanings. This graph essentially shows something similar, but here we took the number of unique signals used in each generation but averaged over a number of runs, and you see that for one mature trainer, the number of signals used doesn't really exceed this. This will be at the upper end, so this will be like generation 50 towards the end. It doesn't really go that far out, and therefore doesn't get very high in terms of compositionality. If, however, we increase the number of mature trainers, we see more signals start to be used, and thus a higher level of compositionality is achieved. In conclusion, iterated learning does seem to work within a population of agents. Achieved compositionality does have a strong relationship with bottleneck size. Language learning can occur in a system where immature agents are training one another, just so long as the number of immature trainers does not exceed the number of mature trainers. And finally, the number of multiple trainers does appear to be beneficial to language learners. And this appears to be due to the fact that there is more signal variety in the training input. And this makes sense, going back to the original concepts of iterated learning. If you, as a language learner, are given a training set which is created by just one language user, then that training set is going to be a very biased sample, because that your trainer is going to have certain biases that favour specific signals over others for certain meanings. If, however, your training set is constructed by multiple mature trainers, then yes, it's still a slightly biased sample, but it will start to even out eventually, because each of the individual trainers will have their own biases which will favour different signals. This then sort of gives you more sort of signal evenness in your training set, which eventually enables you to sort of be sort of more, it gives you a better sample of language and enables you to sort of pass on this, enables you to evolve a better compositional language over time, because each individual is given a better sample of a language. And this does tend to fit in with some of the stuff we've seen in the wider theoretical literature, such as the recent idea that perhaps certain aspects of language perhaps evolved alongside things such as cooperative breeding and allocare in early hominins. But that's a story I've got for another time. For the time being, that's all I've got to say on the matter. Any questions?
Thank you.